In Part 14, the focus was on the subject of equilibrium, the basic theory which allows for the volumetric analysis referred to as titration. Well, in this presentation, the opening topic focuses on what a titration is, the ideal conditions of which will determine a successful analysis, its disadvantages, as well as the advantages for conducting a titration, and the terms that will be used throughout this and the next set of presentations. The subject of titration will be presented in a small set of presentations. I am Rob Boyko, Boyko Mineral Exploration, and welcome back. Titration has been used as a traditional method for the determination of the concentration of an element. It is a traditional, long-standing method of quantitative analysis. It has long been considered as a reliable method for the analysis of the concentration of an element of interest in a solution. The procedure is simple in complexity. A reagent is added to the sample solution which reacts to form a product that is measurable. The concentration of analyte in the sample is not known. However, the concentration of the reagent is known, and by carefully introducing the reagent to the sample to achieve the determined reaction, knowing the volume of reagent used, the concentration of the analyte can be calculated, that is, determined. The reagent is slowly added by the use of a burette. A simplified reaction equation is shown. The capital A is the titrant. The titrant is the reacting compound used. The capital B is the sample solution containing the element of interest. The lowercase a is the number of moles in the reaction formula. This is the same as was shown for the equilibrium equations. It represents the number of moles for the titrant. The lowercase b represents the number of moles of sample analyte. Now there are a number of methods that are used in regards to titration. We have acid-base titrations, coulometric, redox, complexometric, precipitative, are just a few. Then there are terms that describe the reaction type, such as acidometric, iodometric, alkalometric, and electromechanical. Titrometric is also commonly used when the volume component is not calculated or used. This simplified illustration shows how simple the method can be. This is a representation of an acid-base titration, where the sample is added to the conical mixing flask. An acid-base indicator that changes color at the stop point, that is the end point, is added, and a titrant or reaction solution is added dropwise until the indicator changes to a stable color, which signifies the point of equilibrium, which is the end point. However, in order to have a successful titration, there are some important requirements that have to be met. You have to have the correct determined reaction, and it must be stoichiometric. From the reaction equation, the concentration must be measurable. The reaction that takes place must be rapid, and it must be complete. The endpoint has to be well defined for accuracy. This can be visualized by a color change using an indicator as mentioned, or it may be visualized by the formation of the solution turning turbid, that is, turning into a cloudy solution, or a cloudy solution solubilizing, turning clear. Any titrant used must be a standard. If it isn't a standard solution, then it must be standardized for a true and accurate concentration. The titrant and the sample solution volumes must be accurately known. The actual reaction that takes place must have a definite chemistry with no side effects, no contamination or multi-precipitative characteristics. The reaction must be totally selective. If these requirements are not met, your analysis will not be accurate, and therefore totally useless. As previously mentioned, there are different methods or types of titrations that can be performed. For the small-scale miner, prospector, and/or hobbyist, there are 4 types that would probably be used: acid base, precipitation, redox, which is commonly referred to as oxidation reduction, and complexometric. Well, titrations are commonly used in laboratories because they are considered to be more precise than an instrumental analysis when the analyte concentration are high. Titrations are also easier to perform. Cost is also a big factor. Glassware is fairly inexpensive when compared to instrumental equipment. Not to mention, titration is also considered to be the best method for the determination of the major components in a sample. However, titration methods can be labor-intensive. They can be tedious at times, and somewhat time-consuming. The biggest disadvantage is that titration is not suitable for samples with low concentrations of analyte, as endpoints become harder to visualize at lower concentrations. The endpoints are not sharp enough to signify the end of the titration. To achieve a good analysis, the individual conducting the titration not only has to be somewhat trained in the procedure, the skills to do so must be honed. But this can be accomplished by doing and practicing. Regarding the subject of titration, the terms used are sometimes misunderstood. The term titrant has been used many times in this presentation. It is the standard compound in a solution which has a known concentration that is used to titrate a sample. A titrant can be introduced by the use of a burette. However, it can at times be the solution in the beaker and the sample placed into the burette. The result would be the same. However, the indicator chosen may be different. The term titration is simply the process of adding the titrant, that is, mixing the reacting reagent with the sample until the desired reaction is complete. The equivalent point is the point of equivalence between the titrating reagent and the sample. It is the stoichiometric ratio between the 2 reacting compounds. We use pure compounds or substances. That is, we use ACS grade substances for titration, among other purposes. These may be considered as standards, but in most cases, these will also be titrated to quantify the true concentration of the solution. A titer is just a fancy word for the weight of a pure substance in a fixed volume of solution. The titer of potassium chloride, for example, would be the weight of the potassium chloride measured, that is, weighed on a laboratory scale before dissolving the powder in a liter of distilled water. Now, a chemical indicator is a compound which produces a change within a solution or at near the equivalent point of a chemical reaction. This could even be the titrant itself, where a turbid solution may form, or a turbid solution may become clear at the point of equilibrium. Turbid is simply a term that characterizes a cloudy solution. Or it may be a compound that changes color at the point of equilibrium. One such compound, for example, methyl orange, which changes color from red to yellow at the equivalent point. The indicating point in a titration is referred to as the endpoint. It is the point that responds to the equivalent point. Now, this point has a pronounced change, such as a stable color change. It is the point that the titrant is no longer added dropwise to the sample. However, systematic errors may be introduced at the endpoint. These errors differ from the endpoint. They are either caused by adding a little too much or not enough titrant to have a stable endpoint. These errors have been termed as titration errors. Some pure chemicals can be dissolved in still water and can be considered as standard solutions. Now, standard solutions are those, as already mentioned, have known concentrations. However, sitting on the shelf for quite some time, solutions tend to lose or gain in concentration. In order to be successfully used, their true concentration must be known. Therefore, these solutions are titrated by another standard solution prior to use. The titrant used to standardize a solution is referred to as a primary standard solution. An acid-base titration is typically used to determine the concentration of acids. It is based on the reaction between an acidic sample and a basic titrant. For example, the concentration of nitric acid can be determined by titrating with potassium hydroxide. At the equivalent point, the product formed is potassium nitrate. At equilibrium and at the correct pH value, the proper chosen indicator would change color, indicating the endpoint. In a precipitative titration, the sample would react to form a sparingly soluble compound. A common use would be to determine the concentration of silver nitrate solution. The sample could be titrated with ammonium chloride. At equilibrium, a non-semisoluble precipitate of silver chloride would form. The silver chloride would react with the indicator to indicate the endpoint of the titration. Redox reactions are reduction-oxidation reactions. These reactions generally form metallic elements. That is, that electrons are transferred from one species to another. More on these reactions in a future presentation in the series. Complexometric titrations will involve two or more species, one of which acts as the titrant. These will also be covered in more detail in the series. In a back titration, an excess amount of titrant is used to completely consume the analyte of interest. The excess amount of titrant is then titrated with another standard solution to determine the concentration of the analyte in the sample. An organic solvent such as EDTA is used, followed by another titrant. The metallic ion in the second titrant must be weaker than the one ion that reacted with the EDTA, so that the sample ion is not displaced from the EDTA complex during the second titration. These titrations are needed when the metal ion blocks the indicator, or when the metal ion forms the EDTA complex too slowly, or when the metal ion precipitates in the absence of the EDTA. Now, stoichiometry is just another term to use describing quantitatively the relative amounts of a substance or substances involved in a chemical reaction. It involves a stoichiometric reaction, along with its mathematical computation. One example would be the conversion of sodium hydrogen carbonate to sodium carbonate, commonly referred to as soda ash. Now, soda ash is used as a flux material in fire assays. The formula is shown where 2 moles of the sodium hydrogen carbonate is heated to 200 degrees centigrade, which drives off the hydrogen atom to create the soda ash. Assuming a weighed amount of 100 grams, heated for a couple of hours, divided by the molar mass of the sodium hydrogen carbonate. This is multiplied by the 1 mole of sodium carbonate, which is divided by the 2 moles of sodium hydrogen carbonate. It is then multiplied by the molar weight of the sodium carbonate, which should give a calculated yield of 63.1 grams of sodium carbonate. It also shows that there was 100 grams minus 63.1 grams, or 36.9 grams of water vapor and carbon dioxide that was driven off. Using stoichiometric calculations, the amount of water vapor or the amount of carbon dioxide gas may also be determined. Now this concludes part 15 of the series on classical chemical assay for small-scale miners, prospectors, and hobbyists. This presentation was meant to clarify the terms that will be used going forward in the next set of presentations when they will be published. In part 16, the discussion will be focused on the calibration of the glassware that is used. It is a critical step prior to actually conducting a titration. Calibration is used to determine a more accurate volume of the glassware used. I hope that you will be enticed enough to view Part 16 when it becomes published. If you found this presentation interesting or informative, or if you know of someone who would benefit from this presentation, please give it a like and a thumbs up and a share. It is my only reward. I am Rob Boyko, Boyko Mineral Exploration, and I thank you for watching.